Energy, the environment, the economy, and you. The environment. The environment is our surroundings, including natural and human-made elements including air, water, soil, plants, animals, ecosystems, and the climate. It supports life by providing resources like oxygen, food, and water, and regulates natural cycles like the carbon and water cycles. The environment and global warming are directly linked because global warming changes the natural balance of ecosystems, weather patterns, and the Earth's climate. The environment regulates the climate with systems that naturally regulate the Earth's temperature. Forests and plants absorb carbon dioxide, reducing greenhouse gases. The oceans absorb heat and carbon dioxide, thereby acting as climate stabilizers. Ice caps and glaciers reflect sunlight, keeping the planet cool. And weather systems distribute heat and moisture across the globe. Global warming disrupts these systems and affects the environment with rising temperatures that lead to heat waves, droughts, and wildfires. Melting ice and rising seas that lead to flooding and loss of coastal habitats. Ecosystem disruptions that lead to species extinction and migration shifts. Extreme weather that produces stronger storms, hurricanes, and unpredictable climate. Air pollution and health issues that lead to heat-related illnesses and respiratory diseases. Global warming is the long-term increase in Earth's average surface temperature due to human activities, primarily the burning of fossil fuels that leads to greenhouse gases like carbon dioxide, methane, and nitrous oxide being trapped in the atmosphere that is like a blanket that traps solar radiation, which in turn results in rising temperatures, ice melt, sea level rise, extreme weather, and ecosystem disruptions. Global warming is caused by fossil fuel burning, deforestation, industrial processes that produce methane and nitrous oxide emissions, and agricultural production that depends on fertilizers and the raising of livestock that produce methane. The solutions to environmental degradation and global warming are switching to renewable energy, government investment in green infrastructure, and phase out fossil fuel subsidies, improved energy efficiency, use of LED lights, better insulation, and energy-efficient appliances to cut electricity waste. Businesses can switch to energy-efficient manufacturing and smart grids, decarbonizing transportation, electric vehicles and hydrogen-powered transport, public transport, cycling, and walking to reduce fuel demand and sustainable aviation fuels and shipping innovation. Reforestation and afforestation can remove carbon from the atmosphere and would stop deforestation for agriculture and urban expansion. Carbon capture and storage can capture carbon dioxide from power plants and store it underground, and emerging technologies like direct air capture can pull CO2 from the air. The soil and oceans are carbon stores which can be enhanced by regenerative agriculture and enhanced mineral weathering that absorbs CO2 and by cooling the ocean's surface. Agricultural methane and industrial emissions can be cut by shifting to plant-based diets or low-methane livestock feed, better manure management, and rice farming techniques to reduce emissions. Industry and waste management can capture methane from landfills and wastewater, and industrial emissions can be cut by switching to clean hydrogen and electrification. Adaptation and policy changes include carbon pricing and regulations. Carbon taxes and cap-and-trade systems encourage businesses to cut emissions and stricter emissions limits for industries and vehicles. Climate-resilient infrastructure in cities can be flood-resistant, drought-proof, and albedo enhancers. Government can invest in early warning systems for extreme weather events, support climate research, green startups, and sustainable development, and encourage communities to adopt eco-friendly habits. And individuals can reduce energy use by turning off unused devices, use public transport, green salad, adopt sustainable diets, less meat, more local and plant-based foods, reduce, reuse, recycle to cut waste, and support green policies in businesses that prioritize sustainability. The environment and its energy solution. Global warming is a thermodynamics problem. The ocean absorbs approximately 90% of the excess heat generated by global warming. About 60% of this heat has gone into the upper 700 meters of the ocean, 30% has gone between 700 and 2,000 meters, and about 10% is below 2,000 meters. Of the upper 60%, the tropical mixed layer between the surface and about 50 to 100 meters accounts for between 15 to 20% or more of the total heat. The heat of global warming represents about 8% of the combined heat transport of the atmosphere and the ocean, about 5.5 petawatts in the northern hemisphere, and about 10% of the 4.5 petawatts in the southern hemisphere. The poleward movement of this heat is the path of least resistance for heat generated in the tropics, which, in accordance with the second law of thermodynamics, migrates from a hot source to a cold sink like the ice caps. In the northern hemisphere, 78% of this movement is through the atmosphere. In the southern hemisphere, 92%, with the balance circulating through the oceans. The 2019 paper, Quantification of Ocean Heat Uptake from Changes in Atmospheric Oxygen and Carbon Dioxide Composition, measured atmospheric levels of these gases as the oceans warm and released them as a proxy for global warming. The study calculated that between 1991 and 2016, the average warming amounted to about 409 terawatts a year, an energy imbalance of about 0.80 watts per square meter of the Earth's surface of 510 trillion square meters. A joint NASA and NOAA study found this energy imbalance doubled over the 14-year period from 2005 to 2019. A year later, the International Maritime Organization introduced limits on sulfur content for bunker fuel for ships, which subsequently James Hansen and his colleagues estimated increased the global absorbed solar radiation by 30% over the previous 5-year average. The most recent study estimates the Earth's energy imbalance is about 1.41 watts per square meter, which equates to about 719 terawatts. Although this is an average, in the tropics between the 20 degrees south and north latitudes, the intensity of the solar radiation is in excess by about 80 watts per square meter. Since this area is approximately 175 trillion square meters, and about 70% of this area is ocean, the intensity is 80 watts per square meter times 175 trillion square meters times 70%, is the 10 petawatts of solar heat that annually moves poleward. North and south of the 40-degree latitudes, solar radiation intensity is in deficit as the surplus heat dissipates to space. As noted above, a considerable portion of the heat of warming moves through the oceans. The mechanism whereby this occurs is through the radiative forcing of the trapped greenhouse gases, traps heat in the atmosphere, radiating into the ocean. The sensible heat flux between the air and the sea surface, surface currents, and winds distributing heat across the globe from the tropics to the poles, the thermohaline circulation, convection as the surface cools at night, and during the winter sinking the denser water into deeper layers. Wind-driven turbulence stirring up the mixed layer of the ocean, internal waves driven by tides and underwater topography, mixing and distributing heat to deeper layers. Heat diffusion, transferring through molecular conduction and eddy diffusion. Subtropical subduction, where warm surface waters are transported downward along density gradients into the thermocline, and seasonal and decadal variability, like the El Niño Southern Oscillation and the Pacific Decadal Oscillation, that distribute heat within the oceans. Although the ocean is warming, the surface is warming about 8 times faster than the temperature at a depth of 1,000 meters, which is almost universally at a temperature of about 4 degrees Celsius and where the water is at its maximum density. This is leading to the thermal stratification of the tropical ocean, which impedes the mixing of the heat, dissolved gases like carbon dioxide and oxygen, vital to the survival of aquatic life, and the mixing necessary to bring nutrients like nitrates, phosphates, and silicates that are typically concentrated in deeper waters due to the sinking of organic matter following decomposition back into the euphotic zone where photosynthesis occurs. Thermal stratification is a double-edged sword. It can create stable conditions for some organisms in the upper ocean, but it restricts the vertical exchange of heat, gases, and nutrients, thereby creating cascading effects on marine ecosystems, biogeochemical cycles, and the ocean's role in regulating Earth's climate. Also, it creates the thermodynamic conditions for converting the heat of global warming into useful work. Whereas poleward movement is the path of least resistance for heat generated in the tropics, this can be a 10,000-kilometer-long path, whereas the closest heat sink is only 1 kilometer beneath the surface. Thermal stratification impedes the movement of surface into the deep, But the necessary movement is accomplished with a heat pipe that is a passive device that serves as a medium for transferring heat from a high-temperature source to a low-temperature sink over a long distance. It minimizes heat loss to the surroundings and operates efficiently using a working fluid with high heat transfer capability. The conversion of the ocean's vertical thermal energy gradient to electricity via ocean thermal energy conversion, or OTEC, has been demonstrated at small scales over the past century. It represents one of the planet's largest and growing potential energy sources. This technology can be modified to provide a large source of CO2 emissions negative energy while also removing heat from the surface ocean, helping to directly counter ocean atmosphere warming. Several problems are associated with conventional OTEC, including high capital cost, low efficiency, heterogeneous heating and cooling of the Earth's surface, and material availability, all of which are addressed by thermodynamic geoengineering, or TG, a deepwater condenser variant of conventional OTEC that transfers heat by way of a heat pipe. OTEC is a heat engine variant, which requires a heat source, an evaporator where the heat converts a working fluid into a vapor that powers a turbine to produce electricity, a condenser where the spent vapor after transiting the turbine is converted with cold water from a deep water sink back into a liquid that is pumped back into the evaporator to complete the work cycle. In the tropical ocean, the heat source and the cold sink are separated by 1,000 meters of water. With conventional OTEC, this gap is bridged by a 1,000-meter-long cold water pipe, brings cold water to the surface where the evaporator and condenser are located. For a 100-megawatt OTEC plant, the diameter of the pipe is 10 meters, and the bulk of the pipe impacts the size and cost of the surface infrastructure necessary to support it. The ideal sea surface temperature, or SST for OTEC, is 30 degrees Celsius, and the deep water heat sink at a temperature of 4 degrees. Therefore, the theoretical Carnot efficiency is 8.6%. OTEC thermodynamics, however, dictates that only half of the heat is available to produce work at the turbine, because the evaporator and condenser pinch points sap 1/16 of the heat each, and 3/8 each is lost going through the heat exchangers. So, the maximum realizable efficiency is closer to 3.1%. Melvin Pruitt, a Los Alamos Labs theoretical physicist, however, devised a system that uses a deep water condenser and heat pipe he called a heat channel with a calculated efficiency of 7.6% when the working fluid used is ammonia. His calculation was based on a surface temperature of 27.5 degrees Celsius rather than the 30 degrees TG can attain in view of its ability to seek out the highest SSTs. This 250% efficiency gain over conventional OTEC is derived from cutting the losses through the evaporators and condensers of the heat engine by half by using hot and cold water contiguous to the heat exchangers, rather than pumping cold water from 1,000 meters to service condensers at or near the surface. But the biggest efficiency gain is derived from the 5.3-degree temperature gain of the boiled working fluid vapor in a heat pipe under the gravitational influence of a 1,000-meter-long column of gas situated vertically in the ocean. A 1 gigawatt TG plant would use a 4-meter diameter heat pipe to transfer the latent heat of evaporation to the turbine instead of transferring sensible heat with the cold water pipe of conventional OTEC. Beyond this efficiency gain, a 10 times decrease in the size of the connection by the surface and the deepwater cold sink reduces the cost of the systems by at least 30%. Most OTEC energy potential is far offshore. Thus, converting the produced electricity to a chemical energy carrier, such as hydrogen or its derivatives, is required. This can be achieved by employing a proven method of electrochemically generating hydrogen that also consumes CO2, converting the carbon to a common form of ocean alkalinity. Adding such alkalinity to the ocean would provide high-capacity carbon storage while also helping counter ocean acidification's chemical and biological effects. For each gigawatt of continuous electric power generated over 1 year by the preceding negative emissions OTEC, roughly 13 gigawatts of surface ocean heat would be directly removed while producing 130,000 tons of hydrogen per year, avoiding 1.1 million tons of carbon dioxide emissions per year, and consuming and storing, as dissolved mineral bicarbonate, approximately 5 million tons carbon dioxide per year. This CO2 mitigation would produce an indirect planetary cooling effect of about 2.6 gigawatts. Such negative emissions, energy production, and global warming mitigation would avoid the biophysical and land use limitations posed by methods that rely on terrestrial biology. The problem with electrochemical electrolysis is it is expensive. In 2013, it was estimated to cost $154 per ton of direct electrolytic dissolution of silicate minerals for air carbon dioxide mitigation and carbon-negative hydrogen production. In the paper Negative CO2 Emission Ocean Thermal Energy Conversion, it was estimated 1 gigawatt of OEC energy production would sequester 5 million tons of carbon dioxide. Since the capacity of thermodynamic geoengineering is 31 terawatts of power a year, it has the theoretical potential of sequestering 155 billion tons of carbon dioxide at a cost of $24 trillion a year, which isn't economically feasible. Hydrogen is the most elemental chemical and can be derived by the electrolysis of seawater. As the U.S. Department of Energy has pointed out, high-pressure electrolysis can contribute to the enabling and acceptance of technologies where hydrogen is the energy carrier. Thermodynamic geoengineering electrolyzers would operate at a depth of 1,000 meters where the pressure is 100 bar. High-pressure electrolysis requires pressures of 120 to 200 bar at 70 degrees Celsius, whereas the temperature at a depth of 1,000 meters in the ocean is 4 degrees Celsius. And these temperatures and pressures are conducive to high-pressure electrolysis and would eliminate the need for external compression that would otherwise consume about 3% of the energy required for high-pressure electrolysis. Hydrogen produced at 1,000 meters would arrive at the surface 70% of the way, logarithmically, toward the 700 bar pressure needed for transportation applications. Ocean-derived energy systems like ocean thermal energy conversion and thermodynamic geoengineering costing between $2 and $3 billion can produce hydrogen through electrolysis, which can later be converted back to electricity. They would sequester carbon dioxide by cooling the surface and producing hydrogen at no additional cost for these benefits. The oceans have a greater heat capacity because of their higher specific heat and the heat mixing in the ocean's upper layer. TG is a global cooling method deployed at scale that would generate 1.6 times the world's current supply of primary energy and remove carbon dioxide from the atmosphere. The cooling would mirror the ostensible 2008 to 2013 global warming hiatus. At scale 31,000, 1 gigawatt plants are estimated to be able to a. Displace about 0.8 watts per square meter of average global surface heat from the surface of the ocean to deep water that could be recycled in 226 year cycles. B. Produce 31 terawatts, relative to 2019 global use of 19.2 terawatts in C. Absorb about 4.3 GT CO2 per year from the atmosphere by cooling the surface. The estimated cost of these plants is $1.8 trillion per year or 30 years to ramp up to 31,000 plants, which will be replaced as needed thereafter. Compared, for example, to the cost of world oil consumption in 2019 was $2.3 trillion for 11.6 terawatts. The cost of the energy generated is estimated at 8 cents per kilowatt hour. The need to generate vast amounts of clean, affordable energy to meet the demands of a growing population and rising living standards worldwide is going unmet. Technological advances and efficiency gains can lower energy costs, and the cost of everything that requires energy inputs is not being advanced and instead passive-aggressively discouraged. The notion of energy too cheap to meter is yesterday's news, even as costly atomic energy, like all exothermic energy sources that exacerbate global warming with the waste heat of their generation, is advanced. Even as abundant energy cheaper than the environmental cost of burning fossil fuels languishes. Free energy is the thermodynamic state whereby the maximum amount of work can be derived from a system at a constant temperature. Global warming, as the term implies, is a massive oversupply of energy in the form of heat that can be converted to work, and the ersatz waste heat of that process can be sent into deep water from where it will passively diffuse back to the surface where it can be recycled. Whereas waste heat is endemic to most thermodynamic processes, renewable energies that derive energy from the sun do not increase the global radiative imbalance. Therefore, while 60 to 70% of existing primary energies end up as waste heat and hence are inflationary, the most significant baseload source of energy that reduces energy's cost languishes.